Hi everyone! Today I'll be talking about equatorial ocean circulation. As we know, the mean circulation of the ocean is steady and is balanced by three different forces. The first is the pressure gradient force, then wind shear stress, and the Coriolis acceleration. Around the Earth, we can clearly see this interaction in ocean gyres. However, at the equator, the Coriolis acceleration drops to zero. That means that the pressure gradient force and the wind shear stress alone maintain the balance, just like they would on a non-rotating planet. However, it is notable that the Coriolis acceleration does become significant at about 0.5 degrees above and below the equator. So what does this mean for equatorial circulation? Well, to understand the effects of wind stress, let's look at the location of the equator. First, we have the geographical equator at 0 degrees latitude, and then the so-called atmospheric equator, known as the Intertropical Convergence Zone, the ITCZ. While the geographical equator is easy to define, the ITCZ moves seasonally, shifting northward in the northern hemisphere summer months, shown in this diagram by the July ITCZ dotted line, and then shifting southward in the northern hemisphere winter months, shown in the January ITCZ line. Why is this? Well, the ITCZ is actually the region of convergence of the northeastern trade winds and the southeastern trade winds, about 15 degrees above and below. These winds are a part of atmospheric circulation, where cold air from higher latitudes descend and travel toward the warmer equator. On the way, they are deflected westward due to the Coriolis effect. These descending winds are the surface winds known as the trade winds. In the past, these allow easy ocean travel of sailing ships, facilitating trade across the oceans, ultimately giving them their name. As there is more land mass in the northern hemisphere, there is greater heating in the summer compared to the southern hemisphere, leaving atmospheric circulation slightly unbalanced and causing a northward shift of the trade winds. Note here that the southeastern trade winds actually extend across the geographical equator. As these winds blow, they converge near the equator to produce a weak resultant wind known as the doldrums, defining the ITCZ. As the winds shift in position seasonally, so does the ITCZ. Now that we've established the wind forces, let's look at the resulting currents. As there is little to no Coriolis acceleration in this region, the mixed layer of the ocean at the equator simply moves in the same direction as the winds acting on it. About 15 degrees above and below the ITCZ, water flows westward with wind stress from trade winds. These are the north and south equatorial currents. These currents are also a part of the western return flow for mid-latitude gyres in higher latitudes. However, right on the ITCZ, this is not so. This is because the doldrums are very weak and provide very little wind shear stress. In the equatorial ocean basins, the trade winds move most of the water westwards, and upon contact with landmass boundaries, the current deflects polewards. However, some of the flow splits off towards the equator, converging with the flow from the other hemisphere and piling up locally. Combined, the heightened water level in that region, with sea surface levels sometimes up to half a meter higher in the west than the east, causes a current to flow straight down the pressure gradient back towards the east along the ITCZ. This is known as the equatorial countercurrent. Besides this, another type of current occurs in this region. It involves another scenario where the pressure gradient force balances the effect of wind stress. As the southeastern trade winds at the surface of the geographical equator blow water in the westerly direction, the water piles up in the west, setting up a pressure gradient. At the surface, motion is generally dominated by wind stress. However, wind shear stress reduces in magnitude much faster than the pressure gradient force as we go down the water column. This is due to the eddy viscosity falling rapidly within the pycnocline, the region of rapid density gradient. The pycnocline in the equatorial region is very pronounced as the shallow mixed layer above it is exposed to large amounts of insolation as well as fresh water from frequent rain. At some depth, the ocean water is below the influence of wind and water flow is mainly driven by pressure gradient forces. As a result, within the pycnocline, at about 100 meters depth in the ocean, there is a current known as the undercurrent that works to move water back to the east in order to balance the pressure gradient. As opposed to the countercurrent, the undercurrent is located right on the geographical equator and does not usually deviate for prolonged periods. If for any reason the current splits away from the equator at any point, Coriolis acceleration comes into effect, directing it back towards the equator. This works to strengthen the current, which reaches velocities up to 1 meter per second. For this reason, the undercurrent is known to be narrow and very fast flowing. Though there are many topographical and seasonal variations that affect ocean circulation, the countercurrent and undercurrent are features present in all three major ocean basins, characterizing equatorial ocean circulation. Thank you for watching, and I hope this was helpful.